If switch S1 and S2 are open, give the reading on V2. When that is the case, let's look at S1. There won't be any current flowing in this direction. And when S2 is open, there won't be any current flowing in that direction. Why do I say so? The only path is the voltmeter, and no current can flow through that voltmeter. What V2 will be reading is the EMF, which is 6 volts. With only S1 closed, the ammeter records a reading of 0.75 ampere. Explain the meaning of 0.75 ampere. So we know that the current is equal to the charge in coulombs divided by the time in seconds. So if the reading on the ammeter is 0.75 ampere, then this tells us that 0.75 coulombs passes a point in 1 second. Anyway, let's go to 8.3.1. With only S1 closed, calculate the external resistance of the circuit. So let's go ahead and close S1 and see what happens. If S1 is closed, then this 3 ohm resistor and the 1 ohm resistor are parallel with the resistor R. So we can say that the EMF is equal to I multiplied by R external plus the internal resistance. Do we have the EMF? Yes, we do. That is 6 volts. Do we have the current? It is said to be equal to 0.75 when S1 is closed. So we have 0.75 multiplied by R external plus the internal resistance. The internal resistance is said to be 0.4 ohms. So we have 0.4. What we need to do now is to divide both sides by 0.75. We will have 8 is equal to R external plus 0.4. It should be easy to see that R external is equal to 7.6 ohms, 8.3.1. What about 8.3.2? We're looking for the resistance of resistor R. Well, we just calculated R external. We know that R external is equal to RP plus RS, the resistance in parallel plus the resistance in series. So R external, that is 7.6. RP is what we're going to use to find the resistance of resistor R, plus RS, the resistor in series, that is 4 ohm. So if we rearrange this and make RP the circuit of the formula, we're going to get 7.6 minus 4. So RP is equal to 3.6 ohm. Now we can go ahead and find the resistance of resistor R. RP is equal to R1 multiplied by R2 divided by R1 plus R2. So 3.6 will be equal to R1, the total resistance on this path. That is 4 ohm, right? So we're going to have 4R divided by 4 plus R. 3.6 multiplied by 4 is 14.4 plus 3.6R is equal to 4R. So if I take 3.6R to the right hand side, I'm going to get 14.4 being equal to 0.4R. Now I just need to divide both sides by 0.4. I'm getting R being equal to 36 ohms. Right, 8.3.2. Let's move to the question that follows. 8.4. So in 8.4, they're saying that S1 is now open and S2 is closed. How will the power dissipated by the 4 ohm resistor change? Right, only increase, decrease, or remain the same? Explain the answer. So S1 is now open. Let's go ahead and show that S1 is open and S2 is now closed. So we have the current flowing in that direction. Initially, R external was 7.6. Now R external is just RS, which is 4 ohm. So clearly R external has decreased. If R external decreases, then the total current is gonna increase. What will happen to the 4 ohm resistor if the total current increases? It will dissipate more power because P is equals to I squared multiplied by R. R is constant, so if the current increases, the power dissipated should also increase. So the power dissipated by that resistor increases. 8.5, grade 12 learners conducted an investigation to determine the internal resistance of a battery. The circuit used is shown below. By varying the rheostat settings, the corresponding values of the circuit current and the potential difference V2 were recorded. V2 is the voltmeter reading across the rheostat. Let's go ahead and answer our question. 8.5, 8.5.1. From the graph, deduce the EMF of the battery. When the current is equals to 0, when there's no current flowing, the voltmeter is going to read the EMF. So if you look at our graph, when our current is 0, the potential difference is 4.5 volts. So we're going to have the EMF being equals to 4.5 volts. Another definition for the EMF, it is the reading on the voltmeter connected across the ends of the battery when there is no current flowing, just like in our case. Right, 8.5.2, calculate the internal resistance of the battery. Well, we're supposed to use the graph. How are we going to use the graph? You need to be comfortable with derivating an equation for the graph. Well, we know that EMF is equals to V external plus the current multiplied by the internal resistance. So V external is equals to the EMF minus IR. Well, as we can clearly see, our V external is our dependent variable, that is our Y, and our EMF is our intercept, that is C. Our current is what we are changing, that is X, and then minus the internal resistance is our slope. So we can say that the gradient is equals to minus R. Now we just need to calculate the gradient of this graph. Let's take this point as it is easy to read, and this point. Okay, so VF minus VI divided by IF minus II. Right, so what is VF? Let's use this point as our second point. So we have 1.5 volts minus this point, which is 3, divided by IF, that is 5 minus I initial, which is 2.5. This is equals to minus 0.6. So if we divide both sides by minus 1, we're going to get the internal resistance being equals to 0.6 ohms. And just like that, we have answered 8.5.2.